so that you can see this summary report, right? And then this summary report will show you how you design. So this design does not show your pretreatment because we assume that pretreatment is already passed through, and then conventional process, you have your own SDI is around less than 5. So you can design what's the chemical you want to put, hydrogen sulfate, what's the anti-scalant. Then you can go pass 1 and go for pass 2. So you can see the point 1 is the pretreated water. It's already pretreated. And then second one is the just influent after your pH and the anti-scalant added and going through the first pass. So you can see the number. This number will show you what's your flow rate, what's the water quality, and what's your different pressure, everything. So you can see the number 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So let's see the final, like number 1, number 2, and number 9. So number 1, so you have a pressure 0, your flow rate, your TDS. Number 2 is your flow rate, TDS, your pressure is just 75 bar. Then number 9, so number 9 is your permeate. So you have a pressure almost 0, and then your TDS is around 22 milligram per liter, and your flow rate is 250,000 cubic meter per day. So your feed water is around 627,000 cubic meter per day, which means around 40%, 44% of your recovery rate. So you can see how this can be calculated. So you can have all the detail, how many pass, how many stream, number of elements. So you design everything from your RO system, what's the recovery for your, what's the specific energy consumption can be calculated. With RO flow rate is how much your water is flowing. The element you select this one, pressure bus element. The feed water, you have a different feed water size, concentrate, permeate. So you will get the different results of the permeate pressure, permeate TDS, and then you will get the detail of the pass 1, the RO solute. So already you have a different ions like ammonia, potassium, sodium, magnesium. So all the different ions, you put your information as a feed water in your feed water here. And after RO, adjust the pH, concentrate, permeate, so you can get all the data here. So which means in your assignment, so what's the boron concentration? So from 4 p.m. after first pass, so your concentration of the boron is around 0.47. So what's your limitation of your guideline threshold concentration? So you need to consider second pass based on your criteria of this. Also, how the pH change. Also, you can see the RO design owning. After you design, the RO design, you can consider how this has a problem. Because if you have a problem for your design, if you click this summary report, so it doesn't really show any data, or it does not really give any information. Also, sometimes you will get okay, your feed water is too high, your pressure is too low, your flow rate is too high, something like you will get the design owning. So based on that, you have to go back again, RO, and you have to change. Also, you can see the special comments, what's the consult your company, RO membrane company, for advice on application above 35 degree of the membrane, because the too high temperature will damage your membrane. So you need to consult. Also, they will show what's the flow rate in the different element, different recovery rate. Also, you will have all the detail. And because of our first pass has a very high concentration of boron, which means around 4.47. So in your assignment, so you may remember your assignment clearly mentioned about your boron concentration. How do you ensure that you have satisfied boron limit of 0.3 milligram per liter? So you have to also address, okay, we need to show your boron concentration less than 0.3 in this permeate. So that we need the second pass to remove this one and then have your concentration boron second pass 0.07, 0.01, 0.014. So your concentration of permeate, your second pass, after second pass, your boron concentration is very low in your permeate. So that you can suggest your second pass. So you can see all the detailed information from here. What's the solubility? So your length LSI value is more than 0, which means you have a Pauli potential. So in this RO second pass concentration, and the stiff Davis stability index is also red color, which means we need to incorporate some of the anti-scalant. So you can put some anti-scalant in your system so that you can reduce the overall your fouling potential can be reduced, as well as you can also reduce your pH after second pass so that you can have a better fouling potential than now. So that's how you have to consider for your summary result, and then you can incorporate. Here, okay, if you don't want to use your conventional pretreatment process, okay, you want to use DuPont ultrafiltration. So you can change your pretreatment because this is your design. You don't have to follow only in your schematic. You can change the pretreatment as a DuPont ultrafiltration. So you can put the pretreatment as a DuPont ultrafiltration system here. Ultrafiltration here is coming to here, and then you can see the ultrafiltration condition. So you can click here, ultrafiltration. Also, you can design what's your recovery and what's your backwashing, acidic cleaning condition you can incorporate. So you can have a recovery, which means recovery should be very high for your ultrafiltration pretreatment. So this is your seawater coming after ultrafiltration pretreatment, how much you will get. So you can also design from this recommended range and then design cycle interval. And you can also click your result to get your overall ultrafiltration pretreatment followed by reverse osmosis. So it's up to you. You don't have to use ultrafiltration as a pretreatment because our assignment, it's up to you. You can select ultrafiltration or conventional treatment process so that you can only show your software program for the reverse osmosis design. So that's how we can expect from your report. Is it okay, Hala?
Yeah, but just one question. So we have the schematic diagram provided in the assignment guidance sheet, which has only one pass and 3 stages. So do you reckon that we don't need to stick to this and maybe we need to add an additional stage or change the number of to add a pass or change the number of stages?
Can you show where is the stage, what you're talking about? Can
Can
you
I
show
share my
the,
screen?
yes, you can share it.
Yeah. Um, so here we don't have any passes. We only have like 3 stages. So do we
Okay.
need to stick to this or?
Okay, this is just the schematic. It doesn't say any 3 stage or first stage. It doesn't really matter because this is just a drawing, simple drawing I want to show you. But it doesn't mean I want you to draw the 3 stage system, or it doesn't really represent any stage or process. So this is only arrow module. I'm talking about only arrow module.
Okay, so we need to decide how many stages we want and how many passes we want.
Exactly. You can design by yourself. I gave you several examples. So based on that, you can select some of your information, and then you can design based on maybe, we mentioned about seawater desalination. We need a second stage because of the high recovery rate, around 45%. Also, we need a second pass because of the boron concentration or better water quality of the seawater total dissolved solid. So based on these two information, so you can design second stage and second pass.
The recovery rate is 45%.
First pass 45%, second pass around 85 to 90%.
Okay, because this is also not mentioned in the assignment sheet.
Okay, it should mention in your design. You remember I explained the lecture note.
Yeah,
How you can design the second pass, first pass, how many recovery rate on your stage and then second pass. So I think that in the lecture note, you can go back to 10 steps. Do you remember 10 steps
yeah.
I explained? So you can see the step 4 or 5. Yeah, you can see how many stage we need for seawater desalination, 50%, 45% recovery. Also, BWR, second pass has a very low TDS concentration. That's the reason why we have a less, mm, more high recovery rate up to 90% or 85%. So BWR has more recovery rate compared to our seawater first pass. So that's I explained in the lecture note. So you can see step 1, 2, 3, 4, 5, 10, so that you will have a better understanding why we design second stage and second pass.
Okay, thank you. Sorry, just one last questions. I know too many
Yeah.
questions, but you mentioned in one of like the demonstration videos that we need to compare the operation cost with the water cost. So yeah, but it's also like not mentioned in the assignment guidance sheet. So just want to double check if we need that or not.
I don't need that because
Okay.
cost comparison is always very uh, flexible as well as little bit variable, so that you don't have to show that kind of cost comparison. Just you focus on your design of the overall seawater desalination plant.
Okay. Thank you so much.
Thanks. Any other questions? So we have Dinesh. Okay, so can you please review my design and mail? Okay, mail to you and want to know what I need to correct there. Okay, let me open your file, Dinesh. Dinesh, are you able to share your slide? Hello, Dinesh. Hello. Dinesh, can you hear me? Hello, Dinesh. Oh, he's gone. Hello. Can you unmute, Dinesh? He's using phone. All right. Okay. So, okay, I will share your file. Let me share for you. Mm. So Dinesh, he emailed me the one file, which is his own design, what he trying to do. And let me explain what he's so he's talking about he cannot show any summary report because okay, let me share his slide. Okay, this is his file. Can you see his file, everybody?
Yes.
Yes, okay. So this is the Dinesh file. He like to design 225,000 cubic meter per day. And then he want to achieve the product water 90,000. So to get the 250, so he may need around 2.5, 2.5 this kind of the train for the design. So you look at his feed water, and then he put the ammonia concentration, the ultrafiltration, pretreatment, and turbidity. So he put all the detail here. So finally, TDS is 35, and that's his overall quality of the. So if you look at his first pass, so he has 285. Then from here, so you can see that he has a 225 initial feed flow. Product water, he like to have 90,000. So overall, he has a system recovery around 40%. So he has two pass, first pass, second pass. So he like to have a first pass 42% recovery, and then second pass 90% recovery. And that's his overall overall flux, overall concentrate, recycle, the how many bypass, how many permeate the split he has, and then this is the all the detail he has. Then he used the PB for staging. So how many he got? 285, and then elect element for pressure bus 7. So he used the same membrane, and then he look at the second pass. So he wanna put some sodium hydroxide and H2SO4. So he has the very wrong pH. I don't know why he want to put the pH 9, because this will create the more scaling, inorganic scaling. So I think this one is not really necessary. And I think the H2SO4 is okay. And then he has the 66 and 24. Stage 1, stage 2. And this is the value. So we like to click this one. And let's see his design only. And then let's see his summary of the report, how it looks like. So pass 1, 184. He has pass 2, stage 1, 66. He has stage 2, 24. And then his initial flow rate was, let's say, 224,000. And then permeate, he like to have 90,000 cubic meter per day. So which means his calculation is not working because there are serious mistakes. Maybe because of the sodium hydroxide, maybe because of miscalculation of stage 1, 2, and pass 1. Also, miscalculation of his permeate recovery, 19%. So that he cannot calculate his report because his information is not possible to calculate from the software. So in this case, you have to close. You have to completely close your software. And I will open for our previous example, and then how this is different from his calculation, and then example design, and then we will see how we can fix his calculation. So Wave is not responding from software. I'm opening the different example file. Can you see this example file? Can you, everybody can see this one? Yes, that's good. So okay, the Dinesh, he designed 424 here. Okay, it's almost 3 times lower than 600,000 cubic meter per day. So almost 3, and then this permit product water 250. It was around 90. So which means almost 2.5 different value. Let's see how we have feed water. It's very similar information he incorporate, he utilize. And what's the difference is the pass 1. Let's see the pass 1. So here, pass 1, we have 26,000. And then Dinesh file was overall his flow rate was 253 times lower than RO system for this one. And we have a system recovery 41%. So first pass is 41%, 85% recovery. So what happened is that he set up the first element 2,600 to almost 284. So which means his water volume is 3 times lower than this volume, but this pressure vessel per stage uh, is much lower than we expected. So if we divide this one into three, so let's say 800 something. So which means so his first pressure vessels per stage should have been around 800 something, roughly. But he set the 284, which is much lower value. The water cannot pass through everything. So there are a lot of pressure vessel required for his design. That's the reason why when you click this summary report, everything is frozen because it cannot be make a balance of your water flow in terms of concentrate, permeate, as well as some other information. Also, if you see the stage 1, 2, so he has designed the 66 here and then 24. In fact, this is almost 3 times the lower volume, but it's supposed to be have around 300 something, stage 1, and stage 2, 100 something. Lovely. And then his miscalculation of the pressure vessel shows the wrong stage 1 to value to achieve the overall his flux as well as the recovery. That's the reason why he may change his pressure vessel more. And then he has to calculate a little bit more realistic value of the pressure vessel element and all the difference. So when you have a click this one, summary report, so this example file is well designed so that we hope we can get the summary report from the this calculation of all the detail. So you can see yes, we have a summary of the report, what's happening, and then most important thing like a design owning. So if you have some miscalculation, misinformation, and then misvalue, roughly you put, and then you will have a design owning here. So your pressure bus is too 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 low values. So you need to increase you need to increase your flow rate doesn't really go second pass. So you have to calculate the more pressure vessel in your system as stage 1. So Dinesh, so what you have done is a little bit less calculation of your pressure vessel and then element. So you need to increase more based on your flow rate, based on your uh, productivity and the recovery ratio. So you have to change the value, and then you can see. Also, you got the wrong sodium hydroxide. I think the sodium hydroxide, you don't have to increase the pH 9 in your system. Also, here we put the pH 8, but you don't have to put the H2 sulfur in front. So H2 sulfur is good for here, and then you can completely remove. So sodium hydroxide. So let's see how we can change the chemical. Chemical change in the setup. So what's the chemical value? Just pH. pH. pH 25.5 at the beginning. And then we pH value. Change this one. Okay. So I don't want to put the pH here. Let's say pH should be around 7. I have to put this value. I want to deactivate all the pH in the RO system. So which means I remove the pH here, but I put the chemical at the beginning. I just put as it is. But of course, if you like to remove the pH, so you can change the in this value. But when you change your chemical here, so you can change the chemical value from this one H2SO for what's the pH you can control here an anti-scalant in this system. So let's say we just reevaluate it, but I remove this sodium hydroxide. So you can see what's the difference from your second pass, first pass, and then second stage. So you will see your report, how this will have also we don't have any design O-rings here, no design O-rings. Then we change the pH. So our expectation, we have no solubility O-rings. So it used to be a pH higher sodium hydroxide. That's the reason why previously we had a RO second pass. It was red color. That's the reason why they recommend to put some anti-scalant or pH adjustment. But based on our change, so we found out this one has a very good the design of the system. So I think the Dinesh, what you have to do, you have a less number of the pressure vessel. So you need to change based on your flow rate, as well as your second pass also you have a too low value of your stage 1 and 2. So you need to change from this example. It's given in the canvas, so you can download from the canvas so that you can recalculate, or you can try to have a reasonable value of the pressure vessel per stage, and then you will get the good outcome of the design, so that you can get, if a design report doesn't work, which means it's a little bit of unrealistic design in your RO system. So you have to go back and then try to redesign. Do you understand?
Yes, Professor. Actually, I just replicated the values given in the question, for example. And the thing I noticed, another thing is that the flux, it doesn't really change when I use it. I even tried in another example. So the flux that I've supplied, that's from the example given by yourself. So is the flux enough for my design if I change the PV value that you said?
Okay, so you are saying that if you change the value and if you can show the summary report without designing awnings, That's
Yeah.
fine. That's fine.
Okay, but the thing is that I just wanted to try more, try we can try. The problem in my software is that the clocks doesn't really change when I change you know, uh, the percentage of recovery percentage,
Mhm.
but it changed in your example. So that's why also I use your example as a reference.
Yeah.
So for my design error, I understood that I need to change the values of PV, right? Uh,
Right.
and, and I need to change the PS value for NAOS from 9 to 8.
Yeah.
So that's it. Yeah.
Right. That will help you a lot.
Okay, I'll try it. Yes.
Also, yeah, I will send you this file which I
Yeah.
tested, and then you can start from here and then how you compare the overall flow rate, overall recovery, overall pressure
Yeah.
vessel numbers, so that you can get
Yeah.
the. Otherwise, you can design very simple like a 1,000 cubic meter per day or 10,000
Yeah.
cubic meter per day. So you can
Yeah.
calculate based on the 10 steps. So you remember 10 steps we tried together. So
Yeah.
you can put had the calculation and then put into your pressure vessel, and you will have a very good summary report for your system.
Yeah, Professor, I'll request you to send this file to me and I'll check
Yep.
it.
Okay.
And
No
another
problem.
thing, Professor, like for boron concentration, right?
Yeah.
So it's given 5 in the question, and
Yeah.
so we have to just put it in or and check 0.3 in the result or what? If it's
So
less than,
okay. So you are in the report. The boron concentration is 5, right?
yeah,
So just to put the 5, and then you can click the report, and
yeah,
you will see the permeate because our assignment question is it has to be less than 0.3 milligram per liter, right?
yeah, exactly.
So if you click this one, and then from 5 milligram per liter of boron concentration, so you can see the first fast. The boron
Yeah,
concentration is zero point 0.3. It's more than zero
yeah,
point 0.3 milligram per liter, right? So you need
exactly.
the second pass. So we can go
Yeah,
second pass, which means second pass. The boron concentration decreased to 0.14 milligram per liter, right?
yeah,
So this one will be the okay because less than 0.3 milligram per liter of your concentration. So that's
yeah,
the how you can respond in your assignment. So after second pass, your concentration reduced from 5 to 0.31 to 0.14. So you
yeah,
can have a very detailed, you can change your value in this
yeah.
feed water quality and then look at your final report, how this can be changed there.
So another thing, Professor, the question says the total dissolved solid is around 35,000, right?
Right.
So when we input the values for the ions, let's say the cations first, then the total dissolved solid exceeds 35,000. So does it make any difference for our assignment or what?
I think the 35,827 or 35,000 milligram, it doesn't really make any big difference. So you don't have to worry about because of what you're putting is
Yeah,
we may need adjust your
adjustment. Yeah,
balance, yeah, balance of the cation and ion. So
yeah.
just all ion will be giving some sodium and chloride. So you don't
Yeah.
have to worry about this kind of small changes.
Uh, yeah, Professor, another thing that let's say the temperature we input it's between 13 and 20 or something like that, right?
Yeah, yeah,
Uh,
yeah,
so another thing we adjust PS accordingly. We click on adjust PS. So
yeah.
it gives around 5.5, like you can see it's showing 5.5
Okay, this 5.5 is from your
adjustment.
pre-treatment, and then it's while you're receiving 5.5 for your
Yeah,
RO membrane, but you can change the pH from your system. Let's say pass one,
yeah,
pass two. So you can
Yeah.
put the chemical. So we have add chemical or
Yeah, yeah.
add the degassing. So if you click here, so you can change the pH, you can reduce the pH, increase the pH, or
Yeah.
you can add some anti-scalant or degassing. So you can
Yeah.
see the red color. If you have a red color, there are
Yeah.
potential to increase your overall inorganic fouling for your database because this is chemistry. So you
Yeah.
can, let's say you have this much of red color, so we can reduce the pH maybe 4.
Yeah.
So how many we can change? So we can see that the value of your, okay, still same 1, 2, 3, 4, and then maybe you can change the recovery. Okay, recovery, we may have a less recovery. So based on this pH anti-scalant, okay, we can put some more anti-scalant, maybe 10 milligram per liter. So you may reduce the sum of the value and the outside range. Okay, so 1 to 5. So let's put the maximum 5 milligram per liter. So that's the how you can see the LSI value, calcium phosphate after first concentrate, so that
Yeah.
you will have a better adjustment of your pH. So that will be how you can calculate. So that's 5. The pH is you can change the front in front of your arrow, but what you are having here is it's
Yeah.
receiving your water from pretreatment.
So
Okay.
what's mentioned in the question is the pH is around 8.1, right? So what does it mean? It's after treatment 8.1? Yeah.
Where is what? Sorry, say again.
Uh, but in question, it's given like the pH value is around 8.1.
Uh-huh.
So
Okay.
so what
So eight
what
eight
that
point
means?
one. Okay. So 8.1, which means
Yeah.
you
Yeah.
okay. Let's say in your system.
Yeah.
So 8.1 is your feed water. Seawater pH is 8.1. And
Yeah.
then your pretreatment will change the pH 5 or 6. And then it goes to your reverse osmosis. So your 8.1 is the seawater. Overall pH is 8.1. So that's the reason why we adjust the pH at the pretreatment level as a 5.1 or 6. That's the reason you can reduce the overall inorganic scaling issue. So
Okay.
what you are saying is that seawater, before we do nothing, just the
Yeah.
seawater pH is 8.1.
Okay.
Okay,
Uh,
so any other?
and the other thing, it's mentioned the capacity of the plant is 250 milliliters per day, right? So it
Right,
means the product water is at 250
right,
milliliters per day.
250,000 cubic meter per day.
Yeah. Yeah. Okay. Yeah. I got it.
Yeah,
Thank you, Professor. So
thanks.
can you the file? I will.
Yes, I will send you the file for you.
Yeah, thank you, Professor.
Okay, anybody else? Olina or anybody? Do
Yeah,
you want?
Professor,
Yeah.
just what's the value that we should uh, write at the beginning for the feed intake? So is it the capacity, which is also 250,000?
Mm-hmm. You're right, because okay, let's share my scenario. Okay, I hope everybody has mm, let me say let me okay, just If can you see the scenario from this screen?
Yes, yes.
Okay, this is the scenario. So if you see at the end of your scenario, so this is your process of the synergy desalination plant, right? So you need to design all process, especially when you design RO, you can use the wave software. But if you want to use ultrafiltration as a pretreatment, you can also design as a wave because wave software contain your ultrafiltration. But if you want to design dual media filter, so you can just put the SDI less than 5 conventional pretreatment and the RO. So that's okay. So what you're saying is the capacity. We are producing 250,000 cubic meter per day, which means 250 to our targeted production is at the end of your plant, water supply. So we design, as you know, 250,000 cubic meter capacity. Okay. So this is the 250,000. Then recovery, let's say you want to have a recovery 50%, which means you need your initial feed water has to be doubled. So 250 times multiplied by 2 as a 50% of the recovery. So you need around 500,000 cubic meter per day of your feed water. And then after that, you will produce the fresh water, 250,000 cubic meter per day. So that's the recovery. But when you have your pretreatment, RO brine, so you really have a lot of recovery here, so that you need to also think about your recovery will be 45% here. Its recovery is around 95% because of the backwashing and the wastewater treatment, or you have to clean up this filter. So you need to use some of the clean water. So overall, make us simplify 500 cubic meter per day and 250 cubic meter per day is the capacity you can design. So which means you need to design around 500 cubic meter per day your feed water at the initial stage here. Do you understand me what I'm talking about your capacity?
Yes, Professor.
Okay,
Thank
that's great. That's great.
So, Professor,
yeah.
just one question. So we need to assume the recovery rate for each stage, and then based on that, we can decide what is the amount of the feed water, or we can just take it directly as 500,000.
Yes, okay, we can use directly 500,000 cubic meter per day, and then you will get around 250,000 as a 50% recovery for overall process of your desalination plant.
Okay, thank you.
Yeah. Any other questions? How about any other question do you have? No? Is everything perfect? How about Hala, Dinesh, Olina?
Yeah, all is good
all
for
good.
now.
Thank you.
Okay, so if it's all is good, let me stop sharing.